All right, 4 o'clock, 4:01 actually. I'm a minute late, sorry. Welcome back to the last installment of your favorite class. All right, a couple of announcements. First, I found out that I'll be offering the Advanced Composites elective in the springtime. So, if you want to learn more about composite materials, including more laminate theory, sandwich composites, cure kinetics, fracture mechanics, all those good things about composites, sign up for the elective, which will come in the spring. That'll be ME498. It'll be under a special topics heading. So that's coming in the spring. So that'll be exciting. Hopefully I'll actually get to see all of you in person at that time. Yes. Okay. Vaccine trials seemingly looking good. All right. Other announcements. Again, got an ungraded homework on Blackboard. Make sure to take a look at that. It's on lamina failure. Had someone in office hours asking me about that this morning, so good on that person. Your final exam for this class will be a week from today, from 2 to 4 p.m. Almost exactly a week from right now. And we're going to have an exam review on Tuesday night. Okay, so 7 p.m. on Teams. I'll create a meeting for that and invite all of you guys. That's optional. I'm really more or less just going to go over the sort of study guide that I sent out, that qualitative one. It's a little shorter, so probably not as long, but I'll make sure that One Direction plays in the lobby before we start. Okay. So that's about it. Today is kind of nonsense day. Well, not nonsense, but I just kind of want to show you guys some cool stuff. So I posted a series of slides to Blackboard on kind of cool composite stuff. None of the stuff we talk about really today I'm going to test you on. I just thought, since you've been through the composite class now and actually have some vocabulary to understand some of these things, maybe I show you some cool stuff that's kind of happening in the world of composites. So if you kind of want to follow along with notes, that's cool. Otherwise, I'm just gonna just sort of bring the notes in here directly. All right. A lot of cool videos, a lot of talk over today. All right. So here we go. First things first. Lexus basically invented a 3D braiding system so they could make really sweet 3D carbon fiber braided pieces for their vehicles. So they have this video here on YouTube. It's maybe like 2 minutes long. I kind of like it. It's a little bit like promotional, I guess you would say. So Lexus is kind of like trying to, flex their guns or whatever, but it's pretty awesome to see this thing in action. So we can go ahead and do that.
In the pursuit of a stronger, lighter carbon fiber, the hard way is the only way.
The sound cut out for me.
Hold on, I gotta pause this a second. What was that? Are you guys getting the sound or not?
Originally, not now.
You guys don't have sound?
Yeah.
Well, as soon as you changed it, it didn't work anymore. So like it was working. So
and then it wasn't.
Yeah, in the beginning.
Yeah.
Okay.
We had sound before you unplugged your mic.
Thanks. Okay, we'll try it. One more time, okay?
We needed to find a way. The pursuit of a stronger, lighter carbon fiber, the hard way is the only way.
The original concept of the LFA was for an aluminum body over an aluminum chassis. But after a couple of years of testing, our engineers were convinced that that wasn't as strong and as light a structure as they really wanted for the LFA. So they used the newest, most advanced material, carbon fiber reinforced plastic, or CFRP. So we needed to find a way that could make carbon fiber with better accuracy, better consistency, and at a more cost-effective basis. We had to invent a loom, a special type of weaving machine that didn't exist before. It's a circular loom. It's about maybe 2 meters across.
Look at that thing. Are you serious? Like look at all those creels of carbon fibers they got on the side there. They're feeding like, there's got to be 50 creels of carbon fiber, probably more than that, into the side of that machine. And each one of those, there's like 100 heads on this thing that are all kind of crossing over each other, weaving on a mandrel that's sort of in the middle of this structure. That is insanity. Like the amount of development they must have done just to make this is crazy. So, okay, I'll keep going.
6 feet across. And it is able to weave not a flat piece of fabric, but actually it produces a circular weave that comes out of the end of the loom, and it has just the right thickness, the right number of carbon fiber threads at every point to give us all of the structural properties we need for that part of the LFA. By using a loom which is itself three-dimensional, we're already making a three-dimensional object, which then we can just mold and put the resin into and create into the finished part. Where this will pay off down the road is in the future cars that will be even stronger and lighter.
The hard way is inventing a more precise method to weave carbon fiber. The hard way is delivering on a promise of staggering.
Lexus is the best thing since sliced bread. Okay. No, seriously though, good on them. That is impressive. So they got, I don't know if you saw all the individual heads that are kind of like moving around on the braider there. It's insane, like the amount of engineering that went into that, okay? So very, very cool stuff. All right. And even this picture here, I don't even think they're winding on a mandrel. I think this is just like a free braid, which is even more impressive if you're trying to make something to a particular size. That means that like the tension in each one of those wires has to be like particularly controlled so that you're making this to like near net shape, which is insane. Okay. Think about like how hard that would be, like how difficult an engineering problem that is when you have like how many forces that are pulling you in all these different directions and intertwined strands, and oh my gosh, my head hurts. Okay.
I'm trying to think of how complicated it would be to try and arrange all of this, and I'm just stopping because that's going to cause me to have a panic attack if I try to think through it too much.
Obviously difficult. Okay, onwards. Ceramic matrix composites. We didn't talk about ceramics a lot, but ceramics are used where? High temperature applications, okay? Not a lot of high temperature applications that are commonly used in our days, except for jet turbine engines and shrouds for re-entry for shuttles. Maybe some other niche applications, but those are probably the big ones. And so here, this is a ceramic matrix composite blade, one of the blades that makes up this particular engineer. I forget what it's called. It's like the leaf engine or something like that. So you see all these blades stacked in this particular circle. These are all made out of ceramic matrix composites. I particularly like this video because they talk about actually how they make the ceramic, and most of the time companies are pretty proprietary about how they do something like this, but GE here is like pretty open with what they're doing. So in this video, you'll see like the ceramic slurry, you'll see them putting ceramic pieces into a huge autoclave, and you can actually sort of see what an autoclave looks like on video if you haven't really taken a look at this before. So let's go ahead and take a look at GE's video. And they're also, you know, very happy with themselves. Let's just say, drink a seltzer, save a river, okay?
Today, the bulk of a jet engine's weight comes from metallic parts that are built to withstand extreme temperatures generated in the high-pressure compressor, combustor, and high-pressure turbine, otherwise known as the engine core. Our buddy Kevin here is washing off a lightweight ceramic matrix composite shroud, or CMC as we call it. A conventional shroud acts to prevent airflow from leaking inefficiently between the tips of turbine blades and the turbine casing. On future engines, GE's ultra-lightweight CMCs shed hundreds of pounds off the engine, improve durability, and reduce the need for cooling air, resulting in improved combustor efficiency and fuel savings. Kevin and the rest of the team in Newark will help craft 800 parts, just like this one, every day for the LEAP engine, which has amassed more than 3,600 orders in the early days of the program. So what's the secret behind this unique CMC material? Well, you're about to find out. The CMC manufacturing process starts with yarns of thin fibers that are a fraction of the thickness of human hair. These fibers are strengthened by a proprietary coating, which is then passed through what they call a slurry bath, melding the fibers into a rigid tape. The tape is cut into...
All right, so this is an autoclave. So they're putting these pieces here. You see all this Kapton tape here. This is a high temperature tape. They're putting them onto the trolley, which is going into the autoclave. So if anybody had like the autoclave processing as their sort of manufacturing depth document, looking at you right there, this is what an autoclave actually looks like. So it's got this cart on the outside, and this trolley comes out onto this cart, and this door is wide open. All right, so this autoclave is maybe like 4 feet in diameter. Looks like maybe this one's like 6 feet long. In just a second, you're going to see a shot of an autoclave that's like 10 feet in diameter and like 30 feet long, okay? So, cray.
Precise 3D shapes that are sent off to the pressurized cooker, which we call an autoclave. The autoclave heats up the material and sets the geometry of the part. Next up is burnout, where organic compounds are baked out, leaving a carbon-rich matrix surrounding the fibers. Then,
so here's your autoclave. This is a bigger one. This maybe not 10 feet in diameter. This one's maybe 6 feet in diameter. But you see just like how massive this door is. Like this door is made out of steel. Like, how much does that door weigh? It probably weighs like 2,000 pounds, probably more than that. Like, dang, that thing is intense. All right.
It's off to the melt infiltration chamber, where Kurt and the rest of the guys bake the parts to extreme temperatures so that the silicon reacts with the remaining carbon to finally form the CMC. When it's all said and done, the CMC is 98% dense, giving the part its unmatched strength at the high temperatures needed for improved engine efficiency and precious fuel savings.
Okay, so there's cool thing number 2. High temperature ceramic turbine blades. They're talking mostly about the shroud in that video, but the production for the blades is probably very similar. So yeah, the blades obviously look something like this. And then around the outside of the blades, actually on the perimeter of this engine, they're talking about the shroud, which is the ceramic layer that's kind of like on the outside of the blades. And they say that, you know, if air is moving around the ends of the blades and not being contained in the actual blade structure itself, then you're going to lose efficiency. So the shroud is very close to the tips of the ends of these blades, but all of it made out of these ceramic materials, these ceramic matrix composite materials. All right, very cool. All right, onwards. Let's talk about vascular composite materials. So Turisek, you know, you've seen this before, but this is something I worked on when I was in graduate school. So I want to kind of walk through this, and now that you actually have some knowledge and some information about manufacturing, you can sort of respect or understand how awesome this is. All right, so the idea here is that you have some reinforcement mat. Okay, so this is like a 3-dimensionally woven mat of reinforcement. No resin yet in this particular situation. This pink fiber here, this is a sacrificial fiber material. It's actually like a polymer material that will be sacrificed later in the production. And why would we do that? Okay, well, we weave this fiber into the preform, to the, you know, woven mat, and you see a picture of that actually happening here. So these pink fibers are sort of like integrated with the weave of the glass. You infiltrate with resin and you get something like this. So we use Vardum, but you can do whatever process you want, I guess. And so you have these fibers that are in the structure itself that remain after the solidification of the matrix material. Then you raise this to high temperature. We use about 200 degrees Celsius and put it under vacuum pressure, right? So you're pulling vacuum on this thing. And the fiber that's inside here actually sublimates, goes directly from a solid to a gas. And you sublimate it out and you trap the fibrous materials that are kind of coming out. And what you're left with is an internal network of like hollow channels that you can fill with whatever, okay? Fill it with, you know, ferrofluid to make it magnetic. You can fill it with a coolant to keep it cool. You could fill it with, you know, an electrically conductive material, liquid metal, for instance, to make the material electrically conductive, so on and so forth. Okay, a lot of cool stuff. So you incorporate some fluid and you see some fluid passing through these channels here, okay? Very cool. So, like I said, you could do a lot of awesome stuff with this sort of manufacturing, right? So imagine, and this is kind of like how your body works, right? Your body has a series of blood vessels on the inside that do a lot of things for you. You know, it transports nutrients where it needs to go. It heals your body for you. It regulates your temperature. Like, obviously, blood flow is very important in your body. Try to emulate that here in composite materials. So fill it with some coolant to take the temperature from hot. And here we have some coolant that keeps it cold. Could do some chemical reactions on this side, but if you have like two channels that are kind of coming together inside of a composite, they're going to mix inside of this like mixing region. Here we have like the chemicals that were inside of a glow stick that are kind of passing through to create this like luminescence inside the material, which could be useful for something, who knows. Change the magnetic signature by filling with a ferrofluid, like I said. And then could also change the electrical properties by filling with, let's say, like a liquid metal. All right. The thing that I worked on when I was in graduate school actually was looking at using these channels for self-healing purposes. So if you thought about like a composite that had this general structure with these channels inside of it, we're representing here the channels with these blue and these red lines. They're kind of running in like this woven sinusoidal pattern. Let's say that the red channels contain liquid part A of an epoxy and the blue channels contain liquid part B of an epoxy. The idea is if you have some fracture event that might happen, let's call it a delamination event that happens between individual layers, it could spill out the liquid from those particular layers into the crack. So you see the red and the blue kind of meeting in this crack plane, they're liquid components. And if this chemical species, this A and this B, are some polymerization reaction could happen, you could get repolymerization inside of the crack, and basically you're back to nominal. You're back to normal. All right, it's just like the way that your body works. Like you get some damage that occurs on your skin or inside your body, you bleed out. That bleeding clots, you heal yourself, your skin reforms, and in a way you go back to normal. Okay, so that's the idea here. Very cool sort of technology. Like I said, this could also be used for cooling. So we had a friend of mine in the senior design seminar yesterday. His name, 2 days ago, Tony. So he worked on this particular project. This was incorporating channels into a carbon fiber composite to keep it cool. So what you're looking at here, this is a sort of a cross section of a laminated composite, and he's showing here 0-degree plies, 90-degree plies, laminated structures here. So you've got this alternating 0-90, 0-90 structure, and he's cut out some of the 90-degree plies so that he can incorporate some of these sacrificial elements, so that after production he's left with channels inside of his composite that look something like this. So like this here would be a 90-degree layer, and then here you'd also have another 90-degree layer. He's cut out some of the material there so that you've had this channel here instead of that fiber material for the reinforcement, okay? And then obviously across the plane here, these are like the 0-degree layers, all right? So the idea here is he puts this into a mechanical like compression device. These are like anti-buckling guides on the side, and he has a heater on the back side of here. And the idea is he wants to know, can he retain mechanical properties like the elastic modulus while he's heating this sample if he's passing coolant through the composite at the same time? So here's like an IR image of what he might see on his composite as fluids are running through the channels inside the composite while he's providing some compression. So he's like measuring the elastic modulus of this guy as it's being heated at high temperature with this coolant passing through, just so we can verify that the modulus is retained. All right, so pretty cool kind of idea. So what he sees here is results that look something like this. We have a question, Lucas.
What's like how much strength do you sacrifice to add in those channels?
We have a question here. How much strength do you sacrifice to add in those channels? That's a very good question. It depends on how you're loading your structure, right? Because we know that loading in various directions can be have different influences. Unfortunately, we haven't talked too much about laminate strength, but a short answer to your question is the channels do introduce stress concentrations, which is kind of a problem. But if you load in the direction of the channel, basically zero effect. If you load across the channels, much more severe effect. How about that? Okay, so what we're looking at here in these particular graphs, this is a control specimen without channels. So here we're looking at an IR image of a sample that doesn't have any channels inside of it. And obviously we see that it's just like very hot. It's like all red. The idea here is we're providing a certain amount of heat flux. Here's 30 kilowatts per meter squared, 15 kilowatts per meter squared, 5 kilowatts per meter squared. What Tony's showing with this graph is after about like 60 seconds, if you're providing 30 kilowatts per meter squared, your composite's going to reach a temperature of above 200 degrees Celsius. And at that temperature, like you ain't doing very well, okay? If it's a polymer matrix composite, it ain't surviving above 200 C. So what he's trying to show is if I put 30 kilowatts per meter squared on a composite, after about 60 seconds, it's about 200 C if I don't have any active cooling on this guy, all right? However, if I run a similar test where I put, let's say in this graph, he's got 65 kilowatts per meter squared, so almost twice as much as this 30 kilowatts. Yeah, he's reaching some plateau value here, which is like 175 C. There might be some matrix materials that could survive this, okay? So just by having this like active cooling where he's got the channels running through here and some coolant running through here, he's keeping this composite cool and keeping it in a temperature where it might actually be serviceable, all right? So giving you the ability to operate in temperatures that you might not have been able to do before with a polymer matrix composite. So pretty cool stuff. All right, continuing. Another project another friend of mine has worked on, he's now a professor at Purdue, his name's Tyler Tallman. He worked on automatically sensing when damage has occurred inside of a composite material with a technology called electrical impedance tomography. It's a structural health monitoring technique. Okay, the idea here is, okay, let's create a carbon epoxy composite, and maybe let's put in some carbon nanotubes in there to help with electrical conductivity. But the idea is you have this laminated composite structure that's basically made of like carbon and epoxy. And so we can decorate the outside of the laminate with a series of like electrodes. Okay, so that's what these red sort of rectangles are meant to represent. They're meant to represent electrodes. All right, so sort of one side of an electrical pair. The idea here is that you can sort of hook up voltage sources across all of these electrodes and more or less measure the conductivity between one electrode and all of the other ones that sort of decorate the binary. All right. So the idea is that you get this map of what is the electrical conductivity of this piece from one location to another, because your material is made out of carbon and you have the ability to measure some resistance over distance on this piece. So I can look at, all right, this node, what's the resistance to all these pieces? This node, what's the resistance? And if you see an increase, a sudden increase in the resistance from node to node, you can know that between the node that you're looking at and that node over there, some damage has occurred that has interrupted that electrical conductivity. All right. So you can pinpoint a location of damage if you're looking at like, what is the resistance of my piece across all of these electrodes? You can sort of pinpoint where that damage has occurred. And this is a structural health monitoring technique known as electrical impedance tomography, or EIT for short. So Tyler's done a lot of work with structural health monitoring, like very, very cool stuff. All right. Next, carbon fiber 3D printing. 3D printing obviously is like all the rage. You know what I'm saying? For like the last 15, 20 years, it's been like a pretty powerful and pretty kind of interesting manufacturing method. Though it hasn't come to light really in engineering application because like the strength of the interlayer is relatively weak. A lot of people have looked towards trying to strengthen the interface by, let's say, 3D printing with carbon fiber and epoxy at the same time. The closest I've seen to anyone getting viable volume fractions with carbon fiber 3D printing is probably this company here. There is a company called Markforged that does some 3D printing with carbon fiber, but the largest volume fraction I've seen there is about 35%. It's very good, don't get me wrong, but still weak through the thickness, and it's more or less got carbon fibers only in the plane of the 3D print. This is a newer company here, Arrivo, I don't know. They're claiming volume fractions of up to 50% with their process. And their matrix material is not an epoxy, they have a UV curable thermoset matrix. So this is like if you ever go to the dentist and you get a filling, and then they shoot the UV light on your filling. What's happening is that filling that they've put in there is a UV curable material. So they've injected your filling and they're UV curing it with some UV light. The idea here with this bike frame is that they're sort of printing it with like this frame element like on the bed of the 3D printer, and they're building it up, which would be sort of like the width direction of this bike frame. All right. And what they're doing is they lay down fiber and they lay down like a UV resin that's sort of like combined with the fiber, and they immediately follow that that sort of like fiber roll that they're laying down with a UV light. So it's like this continuous process where they're laying down fiber, following it with a UV light to like partially cure it as it goes. So layers are sort of like partially cured, bonding to each other. And then at the very end, they take the entire assembly and put it in a UV oven for some amount of time, probably like a day, to fully cure that UV curable resin on the inside. So they have a cool video that's actually showing this 3D printing process, and you'll see like a purple light that jumps in there from time to time. And that purple light is the UV Here it is. You see some of that purple lighting that's kind of coming in there? That's like the UV curing that's happening like locally. It looks like they're doing some spot curing there, but that's the general idea. And it's cool that you see like at the end of one of these layers that they've 3D printed, they have this like robotic arm here that's kind of coming and chopping the continuous fiber off in preparation to like write the next layer. So I don't know if they've quite perfected the problem of still layer to layer adhesion being, you know, not so great, but you know, they're trying, it seems like. All right, so you get the general idea there. Don't need to play the rest of this. This is, you know, sort of pretty well understood. Okay, get the general idea. So that's pretty good. They claim 50% volume fraction. I'm a little, you know, sus of that, suspicious. But, you know, that's what they claim, right? So good for them. Pretty cool. All right, last thing I want to show off here is this marvel, okay? There's no other way to describe it. These people made a Dodge Charger, 97 Dodge Charger, fully out of carbon fiber, except the frame, the floor, and the front grille. That is amazing, okay? What I also appreciate about this video, the guy actually knows what he's talking about. So a lot of times you get these guys that are, you know, the heads of these companies that don't know jack nothing about making composites. But this guy who's the lead man and talking about the manufacturing process legit knows what he's talking about. He'll talk about things like autoclave processing, bagging processes, Vardum, etc., wet layups. He uses the right vernacular and the right language. He legit knows what he's talking about. So let's go ahead and watch a couple of minutes of this. This is pretty awesome.
Ready to go digital? Cut the cord from traditional injection molding with digital manufacturing.
Got the 1970 Dodge Charger we call Evolution. Ooh. Evolution is not only the name of the car, but it's the process that we built it. So,
not only is it absolutely massive, but it is beautiful. Tell us a little bit about it, starting with the obvious.
The only metal parts is the floor and the frame. Everything else is carbon fiber.
The floor and the frame. Even the structure for the A-pillar and the roof and everything?
This is all carbon. We have a large autoclave, Speed Core's performance group. We build cars, but we specialize in carbon fiber. And this is basically all aerospace carbon fiber we've done in an autoclave, and it's all done with kind of a little bit of a gold tint from Toray. Everything's in-house, and it's kind of the new way that we're designing and building cars. So there's no body filler, there's nothing on it, it's all straight, super strong, stronger than steel. We're trying to change everything, and evolution, yes, it means the car, but it's also the way we're building, using technology, 3D printing, and carbon.
What's the weight difference for the stock tub versus in carbon fiber?
So if you had a regular 70 Charger, say it had Hemi in it, you're looking around 3,900 to 4,100 pounds. So we're about 3,400, so maybe about 900 pounds lighter than factory.
What's different from a stock car? Because I mean, I noticed that the grille surround is a bit shorter, the bumpers are removed or completely tucked.
I used to have a steel chrome front bumper like that with a big gap.
A lot of cars from the era,
yeah. You might remember from Fast and Furious 1, that's the way they kind of looked. So what we did was made really nice tight tolerances. Kind of got rid of the ugly, if that makes sense, with beautiful gaps.
Yeah, look at that.
Amazing part.
I live my life a quarter mile at a time. Don't forget it.
On this, the 70 grill was great. It used to have a flip-up headlights, but we designed this one to look more like a NASCAR kind of grill. So this is actually all carbon fiber, And all this mesh, you see the chevron is going to continue throughout the car in styling. And this is all done out of 6061 aluminum, and it's all machined.
Are these new Demon headlights?
No, actually we got these from JW Speaker. It's kind of a unique LED, and it looks really good with the car.
Yeah,
happy with it.
Cool. It's crazy how the fit and finish on this thing is like, the gap is 100% symmetrical all the way around.
And if you look at the weave orientation as the...
Yeah, look at that weave in there. Okay, you can actually tell that this is a twill weave. It's 2/2 under twill weave. And look, it's like the patterning continues from one piece to the next. That is insane. And this gap is like continuous. I mean, the more you learn about composite processing and learn about like shrinkage around a mold, and the more that you're just like, that's amazing. Okay, it's like the better that you become at golf, the more you can respect Tiger Woods. It's this idea. Okay.
The hood goes through the fender, everything lines up perfectly all the time.
Wow.
So.
I'm not even sure if I want to begin to ask what the process is behind not only just laying up carbon fiber that fits perfectly, but how you actually go about matching up where the weave lands.
Well, there's 3 ways to do carbon fiber. So you can do it in a wet layup form, which is kind of a cheap way of doing it, but it's good for racing. Second way, a lot of people do infusion. Bagged process, the carbon's in there in a mold, and it sucks epoxy from one end to the other, and then it infuses throughout the process. What we use here is the same way they do it on Boeing on the 787s. And this is a pre-preg carbon fiber, and it goes into our molds. We have artisans lay it up and make sure all the lines and the orientation is perfect. And it goes into like a hyperbaric chamber. It's an autoclave. So when you have your weave orientation in the mold, you have to make sure that everything is perfect.
Wow. Okay.
So it takes a real artisan to know what is that angle and how does it come off the roll, and how do you put it in there in the part.
What else do we got here? I mean, we got a carbon cowl.
Yep.
All right, so they continue and go on for quite a while in this video. They show off a lot more pieces, and it's impressive. I don't even want to know how much that car cost. Like, to develop and make all those pieces in the autoclave, 7 figures is not out of the realm of possibility for that car. I'm not joking about that. So, yeah, ridiculous. Okay, so there you go. That's going to conclude my slideshow about cool stuff. Something not as cool that, you know, I also want to sort of draw attention to is a piece that I made recently. Okay, so I sent out an email a couple days ago about a demonstration that I had done. Usually I like to do like one in-class demonstration, but just because of COVID, I can't have so many people in the room and got to keep social distancing. I couldn't have an in-person demonstration this go around. So I did make a piece here. I brought it with me. This is sort of a 10-inch, I think it's 10-inch? Yeah, 10-inch by 10-inch carbon fiber panel. This is 09090 laminate. So this is made out of pre-preg. There's some manufacturing defects on this guy. So I don't know if you see like all these waves on the front here. Maybe the people in the class can't really see them all that well, but there's some waviness that's kind of going on this particular panel. The point is I made a video, a YouTube video on how I manufactured that guy. So if you have interest in actually how some flat plates might be manufactured, I did a very basic demonstration of making this panel. I sent that out in an email a couple days ago. So take a look at it. It's kind of a longer video, but it goes into a lot of depth on what are these pieces that I'm using, what are the consumables that get used, the bleeder cloth, the peel ply, the release ply, the aluminum plates, where did I do it? I did it in an oven. How much pressure did I use? Why did these defects occur in the very end? All that sort of stuff. So, yeah, that basically concludes the course. So, reminder, we're going to do an exam review, which is next Tuesday. I'll do it on Teams. You have your final exam for the class next Thursday, 2 to 4 p.m. Last thing I'll ask you to do, you got about 15 minutes right now. You should have received an email earlier in the week about instructor evaluations. So I make it a point to give time for you guys to do your instructor evaluations. I know like this quarter has not been ideal, obviously, for, you know, obvious reasons, but I hope you guys feel like I did my best to like make it as good as I could make it. All right, like I'm trying to give you live lectures, simulcast if you can't come in person or don't want to come in person. Giving you class notes, PowerPoint. I post these on YouTube in case you have to miss. I'm doing exam reviews. I'm trying to make it as clear as I can what I expect. I'm trying to get your papers and homeworks back as quick as I can. You know, I hope you guys feel like I did as much as I could to make it the best experience possible. So with that, I'll say thanks for coming. Hope you enjoyed the class. If you did, look to sign up for the Advanced Composites elective, which will be offered in the spring. So if anything else, see you guys on Thursday for the final. Class dismissed.